Welcome everyone to this lecture on dimension analysis in turbomachinery. To take you through a vacuum. That's the motivation behind this lecture, is that there are quite a number of innovation that has come on board, more especially in the area of manufacturing. We see where big ships have been designed and manufactured, but it's difficult to manufacture a big machine and test. Thereafter, if you find that it is faulty, you destroy it and make another one. Hence, there was a development where people sat down and analyzed the mean and the ways of coming up with models that could represent or reflect the functionality of the prototype. Hence, this topic can fit in well to allow the manufacturing of these prototypes. Dimension analysis allows the identification of flow around the model. It also has got two areas as we consider the flows, that is dynamic similar or geometric similarity. The non-dimensional ratios or the constants are all equal. That is, for the model as well as for the prototypes, whether the fluid is different or the same, the non-dimensional ratios are the same. In other words, flow around two geometric similar aerofoils in this example, we find that it is the same. Like for the aeroplane, the prototype, the bigger one, and for the model, it will be found that it will be the same. Let us look at the example of an aerofoil. We have seen before the aerofoil, the shape of an aeroplane wing. It has got few parameters which borders on which it shall lift the plane, or the plane how the plane shall move. And there are few things that we are going to look at, especially on the area in which the plane flies, in which the plane also lands. So there are few parameters which we are going to consider. These are forces, velocities, the movement of the fluid around, and these aerofoils. So these parameters, in this case, we are going to call them variables. These variables will be independent or will be just dependent. Independent implies that it doesn't depend on anything. It can exist as independent as it is. That is done. Things like density, velocity, doesn't depend on anything. But things like power is a derived unit, meaning it depends on other parameters for it to be for it to exist. So for the cloud, that is the aerofoil, it has got variables. Okay, that is the chord, the angle of the attack, the free stream velocity, fluid density, fluid viscosity, gas constant, also the speed of sound, and the specific heat ratio. So these parameters, or the variables, they are the one which control the operation of this aerofoil, whether to lift or to lower down. So we are interested in parameters like lift, because we want to see it being lifted off the ground to the atmosphere. So the lift is a dependent variable. It depends on variables which you have just mentioned: the chord, angle of attack, the free stream velocity, the fluid density, as well as the viscosity of the fluid. So the variables, if you look at the variables in relation to coming up with non-dimension ratios, there is a way to come up with these non-dimension ratios which shall be attached to all aerofoils of same family. So this Bankham pi theory, it covers the ways on how to come up with that non-dimension ratios. So first of all, we are going to look at the dependent variable, and we'll look at how many variables does it depend on. So for aerofoil, we have got quite a number of variables on which the lift is dependent upon. So in this case, first of all, we look at what's the number of variables. We count the number of variables. So in this case, where n is number of independent variables, where r is number of basic dimension ratios. You know, in dimension analysis, there are key parameters, okay, which we are going to look at. This is mass, length, as well as time. These parameters, also at some point we can include temperature. These parameters are key in development of any dimension analysis. So as we'll be merging the variables to come up with these dimension ratios, we need to have these basic dimensions, okay, which is mass represented by m, length represented by time l, and then time represented by t. In certain cases, we'll use also temperature, which is represented by theta. Let's move on. So we look at the non-dimension ratio, okay, from these parameters. The first one, it being the speed of sound, okay, which is there. So this speed of sound can be converted into non-dimension ratio, okay, or Bankham pi constant, which is in this case, when we compare the speed of sound to the local speed, we achieve something which we call a Mach number. This Mach number is a constant; it doesn't change. So for aerofoil which has got similar shape, or which falls in the same family, they have got same Mach number. The Mach number won't change regardless of the change of the operation environment. Let's look at the example of the drag. The drag is related to these other variables, whereby using in the Bankham pi theory, you can come up with a relationship of drag to these basic elements like density, the free stream velocity, as well as the chord. So for the drag, it is related to these basic elements using this relationship. The derivation of this relationship, those who had privileged to attend the class had shown how to come up with this derivation, how this u squared came about, and how c came about, all these basic elements. So in the meantime, we'll just consider that the drag coefficient is represented by the drag force and over the dynamic force. Let us look at the application of this dimension analysis or non-dimension analysis to incompressible flow. So in compressible flow, we are looking at situations like a pump, okay? For a pump to work, there are certain variables which should be around: pump, fans, as well as blowers. There are independent variables, okay, which we look at, which comprises of the diameter of the machine, the density of the fluid, the viscosity of the fluid, as well as the speed of this machine. We also include the flow rate of the machine. These are the basic, or the element, or the variables upon which the pump work around. So there is density, there is diameter, there is viscosity, there is also the discharge or the volumetric flow. So these are the variables which are independent. And then to choose which variable will be independent is just arbitrary. You can choose as many as you want, but in our case we are going to consider just these five variables as the area of concentration. And there are also other dependent variables which you are going to look at. That is the total head, the power, the torque absorbed, as well as the efficiency. So for the pump to work, these you have to set the operating point, okay, on which the pump shall work on. Okay, so to change the speed of the motor, the flow, throttle, and other parameters, they also affect the dependent variables. The pressure rise, power consumed becomes dependent function of characteristics of the machine. The characteristics which we are talking about is those variables which are called independent. So we can relate this where we say the head, the total head of the pump is a function of these variables. It's a function of the diameter, function of the rotational speed, function of the flow rate, the volumetric flow rate, density, as well as the viscosity. Also power is a function of density, volumetric flow rate, speed of the pump, density, as well as dynamic viscosity. So to apply the banking power theorem to achieve or to get the constants that will act as a link between the model as well as the prototype, there is a way and there is a formula which you have to apply. First and foremost, we have to count the number of variables that are involved in. So like for the head, to come up with the head coefficient, we need to count the number of variables that are involved in. So from here, from this head formula, you can see that there is 1, 2, 3, 4, 5, 6. So the number of variables involved is 6. So since we are interested in the basic elements, okay, so for us to come up with the variables which shall form the basic element, we have to consider elements which have got the following properties. So the element, one of the elements, you have to combine them such that when you combine the three of these elements should form MLT, that is mass, length, and time. They should comprise a dimension of mass, length, as well as time. So these elements, as we are choosing, the inclination should be based on the element. One of the elements should have the machine properties. That is density. In this case, for the pump, machine property, it will be described by the diameter. And the other element that we ought to consider is the fluid property. Okay. In this case, the fluid property will be described by the density, and also the property regarding the speed, okay, of the fluid. So the speed of the fluid will be controlled by the rotational speed. So these, when you combine the three of these, they will give us the MLT, which is the basic element. So in our case, our basic element will be density, the rotational speed, as well as density, diameter of the pump. So when we get the basic element, which are 3, and then we want to find out how many non-dimensional ratio or non-dimensional group are we going to get from these. So we subtract the total number of variables from the number of basic elements or number of basic variables. So the number of basic variables in this case is 3. The number of variables, total number of variables involved is 6. So when you find the difference there, you get 3. So in this case, we are going to come up with 3 non-dimensional ratios. Okay? That implies that when you're coming up with these 3 non-dimensional ratios, these other dimension, they will be relating to those 3. So in this case, it will be 8 over diameter as well as the speed and the density. Discharge as well as viscosity, these also comprise the other dimension ratios. How to come up out with these I demonstrated in class. So for flow coefficient, okay, when you apply the method of the non-dimension or the dimension analysis using the Bankham-Pye theorem, you will come up with this constant. This constant, it will represent the flow coefficient. It's a coefficient, it's a constant, doesn't change regardless of the size of the pump. If it falls within the same family, then it will have the same flow coefficient. The fluid property, so fluid property in this case, we are looking at the Reynolds number. The Reynolds number is anchored on viscosity. So viscosity divided by the 3 basic elements, we find that using Bankham-Pye theorem, we can find a relationship which reflects as shown. So when this relationship is shown, we can see that this relationship reflects the Reynolds number of the fluid. The other non-dimensional ratios that are involved is power. Okay, so power, the power coefficient in this case will be the power over the density and multiplied by the cube of the rotational speed as well as the diameter raised to power 5. The criteria is the same as I demonstrated in class. That's how we go about finding these non-dimensional ratios. The total head for the pump, we have already described how to come up with the head coefficient, and it can be gotten in a similar way. The head coefficients, okay, most of the time, this is a key and important parameter, okay, when you're analyzing pumps. For most of the times, we'll be facing it, and under the name of called energy, specific energy, okay. So when we are looking at a pump, we look at the specific energy. What's the specific energy of this pump? How high can this pump pump the fluid? Okay. So most of the times when we go to buy a pump, we find that this pump, it has got a nameplate. On the nameplate, there is the head, there is the discharge, but we're more interested in the head because that's the specific energy. How high can this pump pump? Is it 30 meters? Is it 50 meters? So that head is what we are now calling specific energy, because when we multiply that head with the gravity, then we get a specific energy. So in this case, that specific energy is key to us in our analysis. So in the pump family, okay, different pump families have got specific energy coefficient or the energy coefficients, which reflects how the energy is utilized by the pump, or how the pump utilizes its energy to give the energy to the fluid so that it can be raised to heights. So the energy coefficient is represented by this. This is achieved by using Bankham-Pye theorem, as I analyzed in class. Here I can't analyze. I've got no writing pad to show you how to come up with this. But this is the energy head coefficient. The criteria, it was shown in class. So efficiency of turbine is similar. You know that for a pump, the efficiency of a pump is reflected by how much how high are you pumping this water against the energy that is being added by the motor. So the impeller inside the pump is adding some energy. So the energy added by the pump, you compare the energy that is received by the fluid to the energy added by the pump. So the energy added by the pump is reflected as shaft power, and then the energy received by the fluid is reflected as fluid power. So the ratio of fluid power to shaft power is what we are calling efficiency of the pump. Similarly, for the turbines, you can do the same. We know that the turbines is involved in generating energy. Okay, so harnessing energy. When we say harnessing, is the machine is extracting energy. In the previous case, the pump is adding energy to the fluid, but in the turbines, energy is being extracted from the fluid. So that implies that the fluid has got higher energy than the machine which is extracting it. So the efficiencies, we compare the energy of the fluid to that of the energy that is extracted by the machine. So the shaft power, the machine extracted energy to the fluid power, which is energy possessed by what? The fluid. So that way we get what? The efficiency of the turbine. So even for the efficiency, we can still use these coefficients to come up with the efficiency. So you can come up with the power coefficient over flow coefficient multiplied by area of efficiency. These three will give us also the efficiency. The performance curves for incompressible flow turbines is as shown on the diagram. So you can even show the performance curves. In the area lecture, I demonstrated how these curves can be drawn where we have got aid against discharge. But in this case, we are using the coefficients. Okay, this side of the graph, we have got the coefficients which we are calling aid. Okay, and then this side, you are comparing it against the flow coefficients, just like the way we compare aid against the flow. So we can compare anything, power against the flow, efficiency against the flow, aid against the flow, and plot a diagram. But in this case, it is just the constants. Okay, just the constants that you can plot in a similar way as we used to plot for aid against the flow or power against the flow. Okay? These are design points for any machine. Any single machine can be designed. And once you have got these non-dimensional ratios or constants, you can predict. That's the pretty part of these non-dimensional ratios. It's about prophesying what will be the performance of the other machine. Okay, if I've got the machine with a smaller diameter, okay, and then I've got a relationship of that smaller diameter with these non-dimensional ratios. When I come across a bigger diameter machine or a bigger impeller, I can easily determine what will be the aid, what will be the discharge based on these non-dimensional ratios. So it gives us a leverage to predict the geometric similar machine. For a geometric similar machine, you can predict the performance or the functionality of these other machines. So we just analyzed the dimensional analysis for incompressible flow, but also for compressible flow. That is the flow which has got a Mach number above 0.3. 0.3 above 0.3, the flow is considered to be compressible. So flows like those which are considered in compressors, steam turbines, those flows are compressible flows. They've got a Mach number greater than 0.3. So how do we go about analyzing the dimensional analysis for this? So area we had parameters like diameter, we have parameters like density, we have parameters like speed, okay, which is reflected by n. But for non-dimension ratios, those parameters or variables, we will bring in some variables, okay, like specific speed, okay, in this case, which is represented by a subscript 01, okay, this is just a specific speed. And then for the density, instead of using density, we are going to use the mass density, okay, or the mass flow rate, and these other parameters will still maintain. So we will see that the specific energy, okay, in this case, especially for compressible flow, is replaced by the pressure ratios, and the flow coefficients is represented by the mass coefficients, or the mass flow coefficient. For power, is still the same, maintained. So this Mach number is represented by this speed, that is speed. Okay? This is tangential speed or local speed against the speed of sound. This is a flow coefficient. This is an important parameter in actual flow machines. This one is very important, where you define the relationship between the mass as well as density, the machine parameter, as well as the speed. So as I earlier alluded to, these, as we are choosing the basic element, we look at the few properties. Does it have the fluid property? Does it have the machine property? Does it have the flow property? So if you look at it, even for compressible flows, the density is reflected there to represent the fluid property. The diameter is represented there to is shown there to represent the machine property. As this supersonic speed, or the speed of sound, it is representing the flow property. So we're going to maneuver around these properties and come up with dimension ratios, non-dimension ratios for compressible flow. So for the mass, it's shown. This is Mach number for compressible flow. This is the Reynolds number for compressible flow, and this is a specific lift ratio. It's always a constant. Okay? So in this case, the dependent variables will reflect these pressure ratios reflect the specific energy. We know that specific energy, or the enthalpy in compressible flow, the specific energy is represented by enthalpies. So the enthalpy has got a relationship with the pressure. So these pressures represent the specific energy, or the enthalpy of the fluid. And then in the middle here, we have got the relationship of power of the machine, whether steam turbine or the pump. The power of this machine is represented by this coefficient, and the efficiency as well. The other parameter which you have just left out is the mass flow coefficient, or the flow coefficient, which is represented by the mass there. So you can go further. And expound it, and show how these density is replaced by these pressure, as well as the gas constants and temperature. You see the supersonic speed represented by the specific heat constant, the gas constants, as well as temperature, and then the diameter is also maintained. And then there we've got the mass flow rate. So we can maneuver around and play around. We see we come up with this kind of formula. But what is key and important to us is to know the dependent variables as well as the independent variables, so that we can come up with these constants or non-dimension ratios, which shall link the machines which are in the same families. Okay? So you can see from the previous slide that the specific energy, the power, the efficiency is a function of these variables, or the function of these variables. Okay. So these are just some curve representing the mass flow rate, okay, against a specific energy, which is in this case represented by the pressure ratio. Just similar to the incompressible flow, we had the edge coefficient there and the flow coefficient there. So these are just the parameters which are just changing, and then we see some curves, okay, obtained for the same family. The efficiency of pumps, we know that pumps are related, okay, the efficiency is anchored on how much has water received against the energy added. So in this case, it's mass flow rate multiplied by specific energy. We have got the energy possessed by what? The water, the energy added to the water. And then there we will divide it with shaft power. But this efficiency can be achieved using the constants that we have just derived, okay? Those constants, which is flow coefficients multiplied by head coefficient, as well as divided by power coefficient. So when you work out these, you find that you achieve the efficiency of a pump. Okay? These are just some of the curves for independent variables, like for specific energy, represented by pressure ratios. Now we have just come to an important part of our discussion, especially in the dimension analysis, the selection of machine. This part reflects on how you go about selecting the machine. This one is very key. In industry, as an engineer, you'll be employed upon to find, say, a machine has got a breakdown, or the machine has got a fault, or the machine has failed. You need to replace that machine. And an engineer will have to find means of how to go on the market, find a suitable machine for your duties. When I say duties, I imply what is your aid. Okay? In the case of pump, say you are working underground, you are a mine, you are working with the mines, and then the machine underground has got a fault or it has failed. And then you are employed, or your supervisor or the head of the section requires you to find a replacement for that machine. Hence, first and foremost, before you could go on the market to look for a replacement, an engineer sits down first and put down what are the duties. Okay, what is the pressure aid? What is the aid against which the pump was working? What is the discharge? And what is the speed of the motor? So when we consider all these parameters, these are the parameters which will determine the duty. So these parameters will help you to select a suitable machine for this duty. So these turbo machine designers often face challenges because of different machines have got different duties. So for you to decide what type of machine will be the best for this duty, you have to sit down, analyze, and go on the market to choose the machine. So at the outset of the design process, some overall requirements of the machine will usually be known. Okay? So before you could even select a machine, that's like I earlier alluded to, you could even design, those who go into design, those who go into buying, you need to know some of the requirements. Okay? The requirements imply the duty. Okay? So in the duty we have got things like aid. What's the aid requirement for the pump? What's the flow, volumetric flow, or the volume flow rate? What's the rotation speed? Those are the things that you require to know before you could go into design, or you could go into buying anything. In contrast, if you are working for the airline company, these which are involved in flying planes, they normally use gas turbines. So in such places, before we could go on buying or designing a new turbine, a gas turbine, we want to know the duties for that turbine. Okay, so there are few parameters which borders on the operationality of these turbines. So in this case, for the turbines, gas turbines, for compressible flows, we consider the mass flow rate, the specific work, in this case, which is the entropy, as well as the preferred rotational speed. So in order to achieve the easiest way of selecting or coming up with this design, there are two parameters which are prominent, which are cardinal in achieving these. These two parameters is specific speed as well as specific diameter. These are often used to decide upon the choice of most appropriate machines. So the specific speed is derived from non-dimensional group. That's like that we are the area derived some specific non-dimensional groups. Those groups, they can help us now to select which machine is suitable for the duty which we want to carry out. So it's the specific speed that is called specific because it's so specific that when you come up with it, it will be to help you to come up with the right or select the right machine for that duty. So it's defined in such a way that the characteristic diameter, okay, of a turbomachinery is eliminated. The value of NS gives the design or the designer a guide to a type of machine that will be provided, okay, or that will provide the normal requirement of high efficiency at the design condition. So when you sit down to analyze the duty, say the specific speed, the speed of the machine as well as the flow rate, these parameters will help you to come up with a specific speed. So this specific speed will help you to get a machine which will operate at higher efficiency, because these specific speed are always obtained at higher efficiency. So if you obtain, say, for the pump, you obtain a specific speed, and then you go to get this machine, there is a guarantee that this machine will operate at high efficiency, because that's what it was designed for, to operate at those high efficiency, provided the operation or the design condition are met. So let's consider hydraulic turbomachinery with the fixed geometry. That is, the design is not changing, or the impeller is not changing, the diameter is not changing. So in such a case, for us to achieve a machine or to get a machine which was going to give us high efficiency or maximum efficiency, then we need to come up with the flow coefficients, the power coefficients, as well as the eddy coefficients. So these coefficients will help us to come up with a specific speed which will help us to get that machine which will operate at high efficiency. Normally, these turbo machines, they are classified in two families. Okay, so each family has got a range of specific speed. It may have 0.3 to 0.5 maybe. That's the range within which the machine can operate. That's the range within which the machine can have higher efficiency. So we have got, like in this case, this scale reflecting the efficiency against of different families, like family A, family B, against the flow coefficients. It has got this shape. Family A has got this shape, and it has got the maximum efficiency at this flow coefficients, and family B has got the maximum efficiency at that point or that flow coefficients. So to come up with the specific speed, it's a simple matter. You just have to combine these coefficients that we have just described here. Okay, the flow coefficients, the edge coefficients, the power coefficient. So for us to come up with a specific speed, we combine the flow coefficients with the edge coefficients so that we can come up with the specific speed. So as we are combining these two coefficients, our goal and our quest is to eliminate the design parameter. The design parameter in this case, it will be the diameter. So that diameter, we want to get rid of it so that we just have one parameter which will help us find and to get that suitable that machine which will be suitable for our duty or our operation ability. So for us to achieve that, we see a situation where the flow coefficients, we power the flow coefficient to half and the edge coefficient to 3/4 so that we can get rid of the diameter. Once the diameter is gotten rid, what remains is what we are calling the specific speed. So this is the specific speed for incompressible flow. And then for power, like for turbines, that one, the area specific speed, mostly we apply it to turbines, to pumps. But for turbines, where we are more interested in power, we also need to find the specific speed that will guide us to finding that suitable machine which will give us higher efficiency. Okay, so for turbines, the specific speed we relate the power coefficient to the edge coefficient. So our quest is to eliminate the diameter or the machine design parameter. So in this case, we will eliminate diameter by powering the power coefficient to half and powering the edge coefficient to 5/4. This is a resultant, and this is what we call the specific speed or the power specific speed. Okay. So similarly to specific speed, to form the specific diameter, just like we did for specific speed, we eliminated diameter. In this case, we are going to eliminate the speed, okay, the n. So we are going to relate the edge coefficient to flow coefficient. So this d, or the specific diameter, it implies that the machines which has got the same specific diameters, regardless of their size, okay, regardless of their size, you can maneuver around, and same family have got same specific speed. You can come up with any diameter which will give you same operation point. Okay, same operation point. So you can play around with duty, such that when we maneuver around with duty, provided we have got same specific diameter, you can come up with a diameter which is suitable to give you that duty. Okay, provided you are using the same family of turbo machine. So this leads us to the research which was done by Cordia, okay, in 1950s, on how to come up or relate the specific speed to specific diameter. So this fellow did quite a number of experiments, okay, experiment of same families, and he experimented on how the diameter of this machine relates to the specific speed, and he came up with the curve. Okay, so these specific diameter in relationship to the specific speed, it was plotted so that you can achieve the best efficiency for specific duties. Okay, so this is a diagram reflecting the specific speed to specific diameter. So different families, centrifugal pumps, this is radial, mixer flow, axial flow pumps, axial is the compressors, have got different specific speed as well as specific diameters. So we know that, or it's given that specific speed is defined at a point of maximum efficiency of a turbo machine. So it becomes a parameter of great importance in selecting a type of machine required for a given duty. Since it is determined at higher efficiency, everything in engineering, we want any machine to operate at high efficiency. We don't want to be putting more energy and receive the little output. So any machine should operate at high efficiency. So this is why specific speed is an important parameter in that it is gotten at higher efficiency. So in the quest to come up with a specific speed, you see a situation where maximum efficiency condition becomes more important, that it replaces the condition of geometric similarity. Okay? Geometric similarity implies that the shape, the sizes of this machine. So we're interested in more into the efficiency, not into the sizes. So the sizes may die a little, but as long as the machine is achieving or is working at high efficiency, then we can get that machine. So we play around and maneuver around in specific speed so that the machine can. So in an event that you change the specific speed, the machine design also changes, because you know that the machine specific speed is related to specific design, specific diameter. So if you change the specific speed, automatically the design changes as well. So in designing anything, first of all we have to establish the specific speed. So once the specific speed is established, then you can go up and design, say, the size of the turbine, the size of the pump. Because once you design, you have the specific speed. Whatever you're going to design thereafter, they will be maintained, because that specific speed will help you. It is gotten at high efficiency. So we are more interested in efficiency. So whatever is going to be designed under that specific speed, it will produce a result which is at high efficiency. So we know that each different class of machine has its optimum efficiency. Okay, so it has got narrow range, small range, just like I have the area alluded to, that different families have got small range of specific speed within which you can select the specific speed. The figure in the next slide shows a range of specific speed appropriate for different types of turbines or turbo machineries. Okay, so specific speed has must be applied to the design and selection of low speed and hydraulic turbo machines. However, the notion of specific speed can equally be applied to compressible flow machines, and is particularly useful for determining whether a machine is radial or axial flow machine. Okay, is best for the particular requirement. Okay, according to this fellow in 2006, for high-speed machine, the hydraulic machine definition is simply expressed in terms of parameter appropriate to compressible flow. So specific speed, we compare the ratio of the flow coefficient to the head coefficient. Okay, this one is for incompressible flow, but for compressible flow, we replace the discharge there, okay, or the volume flow rate with mass flow rate over density. So this is just the same as the volume flow rate. Okay, and then the specific energy, that's what I alluded to say the specific energy for compressible flow is represented by the stagnation enthalpy, okay, the enthalpy or the stage enthalpy. So this is replaced by the enthalpy there. So this, for compressible flow machines, we use this specific speed. This is a graph showing the range of different families of machines and their specific speed. For a Pelton wheel, the range is from 0.5 goes all the way to almost 0.2. There's Pelton wheel multi-jet, the Pelton wheel single jet, Francis turbine has got this range. So when you have got duty, you have got air, you have got discharge, volume, flow rate, you have got speed. You can compute the specific speed and come to this table and see which family does this machine I'm about to design falls in. So it will show you, okay, if it is a pump, you will know the range of the specific speed, and then you know also the type of pump which you are designing. So before you could go on and select something or make something, you should know this specific speed, which pump is suitable. Is it mixed flow? Is it propeller? Is it centrifugal? Is it radial? Depending on what the specific speed or the duty which you have put down. Yes, with further clarification of turbo machine. Okay. Let's further clarification. So this brings us to cavitation. Even in dimension analysis, cavitation has just fused in because there is a parameter which falls under dimension analysis, which is key to cavitation. Hence, we are discussing this cavitation topic under dimension analysis. So, cavitation, what is cavitation? Cavitation is just the formation of bubbles, okay, in the fluid under low pressure. When the static pressure falls below the vapor pressure of the fluid, then bubbles start forming, and when these bubbles, which forms under low static pressure, they are swept into places where there is high pressure, then the bubbles are compressed and they burst. So that bursting of bubbles is what we call cavitation. So that rapid vapor cavities, the jets that comes from those bubbles will go and bang against the walls of the pipes. That's why this cavitation is important in any design, especially where fluid flow is concerned. Whether it being water utility company, it being underground water line, it being in normal flow of things, cavitation has to be taken care of first from a design point of view. As a designer or engineer who is setting up a system, you have to consider that to ensure that the cavitation aspect is taken care of. So this is called cavitation and should be avoided. It's like a disease. Cavitation is a disease to pipes. Cavitation is a disease to turbo machines, whether pumps, turbines. If these machines, if they are experiencing cavitation, then they won't last long. They will die. They will fail. So the pressure waves which are produced by bubbles, which collapses, is of great magnitude, of order of 400 megapascals, which is so great. So they are small jets, okay, at microscopic level, small jets which comes from those bubbles. They move at higher velocities, or at that higher velocity, when they come against the wall, they start pitting, they start like eating up because of that high impact from that jet, small at a macroscopic level. That's why you see the pits on the blade or on the pipe side, you see those pitting erosion taking place because of those high velocity jet coming from the collapsing bubbles. So in order to prevent this cavitation from taking place, we need to take care of some parameters Okay, so in this case, the net positive suction head, okay, in this case, net positive suction head has to be taken care of. If the net positive suction head, the suction pressure, the pressure at the suction point is lower than vapor pressure of the fluid, then cavitation will take place. So hence, we are bringing in the net positive suction head to taking care of the cavitation. If the suction head is greater than the vapor pressure, then you experience little or no cavitation. So from this formula, this head is called suction specific speed. Okay, so suction specific speed is represented by the head. This is suction specific speed head. The head there suction vapor head. Okay, sorry for saying that suction specific speed. This is suction vapor head, which is represented by the head, absolute head, which excludes the static head, and then subtracted by the vapor pressure of the fluid. Each fluid has got a vapor pressure at different temperatures. Like water has got a vapor pressure at different temperatures. So there is a graph which will help us to find these vapor pressures at different temperatures. So to find such the suction vapor pressure, we subtract the vapor pressure from the absolute pressure. The absolute pressure comprises of the atmospheric pressure, also the dynamic pressure. Dynamic pressure, in this case, we are looking at the losses which comes about as a result of flow. Okay, those losses, because those losses are anchored on the flow speed. So when you take into account of these, you come up with the absolute pressure, and then this is just a vapor pressure. Okay. So the important parameter, just like we are discussing for incompressible flow, for compressible flow, the important parameter specific speed for selecting a machine. Also, as you are selecting a machine, you should know that the suction specific speed for the given machine is as whether it has to be, should be like for pumps, it should be of certain range, and for also turbines it has to be certain range. So for specific speed for suction for suction head, it is given by the ratio of flow coefficients over the head coefficients. But in this case, the head is not like that natural head to which the pump shall pump. But this time around, we are considering the suction head. Okay, by considering the suction head, so that we can come up with this speed. Okay, so this head, it will help us to determine whether we have reached the threshold of cavitation. Okay, whether the cavitation has reached the inception point or not. So this specific speed, okay, in this case we are calling is what we are calling SI, which is the inception of what cavitation corresponding to critical value of suction head. When S is less than SI, okay, that is the inception. I is for inception. When S is less than, that specific speed is less than the inception specific speed, then no cavitation will occur. But when specific speed, okay, which is implies that specific speed of vapor, suction head is greater than the inception specific speed, then we experience cavitation. So for a pump, the inception speed or inception specific speed is in the range of 2.5 to 3.5. For turbine, the inception specific speed is in the range of 3.5 to 5.0. So it is, in most design, it is difficult to come up with the net positive suction aid required, because net positive suction aid required is something which the manufacturer should specify on the characteristic curve. So to come up with that, people had sat down and come up with some relationship. So former cavitation parameter, okay, represented by this parameter. Former cavitation parameter is also sometimes used. It is difficult to come up with net positive suction energy required. Hence, the easier method or simpler way to come up with this is where we compare the specific energy of the machine to the former number. So specific speed of a machine is related to former number. So once you know the specific speed of the machine, you can find the former number. We also know that we know the specific energy of this machine. So we have the former number and the specific energy of this machine. It will be easier now for us to find what the net positive suction energy or suction head required. So thereafter we can know that the threshold or the critical suction head which we need to have is this, based on this relationship. So hence the former suction cavitation parameter is important in the analysis of the cavitation. Okay. So, like I already alluded to, specific speed is only applied to specific family. So, since we are using specific speed to come up with a former number, hence the machine to which these former numbers should be applied should be geometrically similar family. Okay? So you can have different families, you have different former numbers. Okay? Since cavitation is a danger to the machine, checking for cavitation should be a normal part of selecting a hydraulic machine for a particular duty. So every time you're about to get a new machine, you always look at the cavitation, okay, of this. There's always a graph at the bottom of the characteristic curve which shows the cavitation of that particular net positive section head required. So that next net positive section head required, it will help you at different operating points what is a net positive section head required, so that you don't experience cavitation or reduce the cavitation. So this is the relationship which shows the former number to specific speed. So from here we can get a specific speed from the duty and then use it to find the former number. The former number will help us to find what is the required suction head, okay, for this machine. So once you have the required suction head, you buy the machine, and then the system has got this one head which we call suction net positive suction head available. Or you can either use net positive suction head or net positive suction energy. It was just recently changed to suction energy, but it used to be called net positive suction head. Here you've got net positive suction energy, okay, against the flow. So net positive suction head available, it normally reduces with the increase of the discharge. Okay, so as the velocity of fluid increases or the discharge increases, the losses, because we know that the losses in a pipe, in a machine, are direct proportional to the square of the discharge or the volume flow rate. So the losses increases, hence the energy, the net positive suction energy reduces. The net positive suction energy required, it takes up this curve, but the point where these two curves meet, the net positive suction energy available, net positive suction energy required, where these two curves meet, that point, that's a point we are calling critical point. Okay? Before that point, no cavitation. After that point, cavitation begins. This is an example which I gave you, and I gave it to you as an assignment. I've seen your assignment. Most of you have done a good job. There are some are just copying and pasting. So take out this assignment in this example on and see how best you can answer this. Don't just copy and paste, because once you do it on your own, you are better off giving in an exam. However way I'll bring the question, you understand it. So this brings us to the end of the lecture. I'll see you next time for our next presentation. God bless you.